Okay, so today I will show you how to create a custom pitch and roll indicator for your vehicle, for your car, or pretty much anything that you might be driving. And not only I will show you how to put everything together, but of course I will also show you how you can use the images of your own car to create custom gauges that are one of a kind. And as I talk, you can see that I'm tilting this sensor to show different pitch and roll values on those two round displays. And those are not just the displays, those are actually full development boards because they also included the ESP32 S3 microcontrollers. Now you can get those displays with this metal CNC enclosure, but there is also a version without the enclosure that looks like this. And this setup is a little bit messy because there are wires everywhere, slightly blocking the displays. And that's because I'm using those PCBs that are converting pins with the 1.27mm spacing into pins with 2.54mm spacing, which is the common spacing for breadboards, Arduino and so on. And it's a spacing that's much easier to work with. Now those PCBs are not custom made, you can get those on AliExpress for just a fraction of the dollar, and the nice thing is that they came already pre-soldered with those header pins. As you have seen, the final product is much cleaner, and that's because I'm using the custom PCB that is doing the very same thing, that is converting small pin header spacing from the display board to a bigger pin spacing, but those custom PCBs are made in a way that they are not sticking out of the board, and as you can see, I have also used screw terminals, so the connection is a little bit more permanent. Those PCBs were made by PCB YOU, who is also a sponsor of today's video. And if you ever need PCBs, you can use the link down in the description and you can get 10 PCBs like this for free, only paying for shipping. But PCB YOU offers a lot more services, including the PCB assembly, SMD stencils, or even things like 3D printing, CNC machining, or even injection molding. So if you ever need services like this, make sure to check the PCB YOU website. So thank you PCB YOU, and let's get back to our project. And this is actually not the first time that I'm using those displays. I already have a video about the custom boost pressure sensor where I have used the very same displays. Now you should definitely watch that video because today I will not be starting from scratch, but I will actually start with the sketch from that boost pressure sensor project. Also, just a side note, if you are looking for some simple pitch and roll indicator project, I have that one as well. In this one, I was using the microbit board together with the next gen display, and both of those devices are aimed more for beginners, which means that you don't have to write a lot of code, but at the same time you can still use the image of your own car in this project, so this is something for you if you want to start simple. So let's finally get back to our project. Again, I'm using this display board from Waveshare that has the ESP32 S3 microcontroller and the round LCD display with the resolution of 240 by 240 pixels. And since I know from the last time from the custom boost pressure sensor project that I can draw images on the display, the first thing that I want to start today is to get the pitch and roll values. And the good news is that the board itself has the IMU unit, the accelerometer and the gyroscope unit, so in theory we should be able to get those values without any external sensor. The bad news is that I wasn't able to get any accurate values. I mean, I was getting some values, but they were all over the place. So instead I will use the external sensor, and that's this one from the DF robot. It's fully enclosed, slightly bigger and slightly more expensive, but it should give us values that we can directly use without doing any filtering or any advanced post-processing stuff. So let's start by opening the documentation for this sensor. Inside here you can read that the module should work with 3.3 volts, which is the ESP32, as well as with 5 volts, which is for the Arduino. And it should be very precise. You can see some crazy numbers like 0.05 degrees. And it's sending the data using the TTL communication, using the serial communication, which you can also tell by seeing the RX and TX pins, or simply by the name, which is called the serial 6-axis accelerometer. If I scroll down in the documentation, there is a connection being shown for the Arduino Uno, as well as some sample code for the Arduino Uno, but just because I see some ESP32 in the code, it makes me think that it should also work with the ESP32, so let's actually try that. I will copy the code into the clipboard, then open the Arduino IDE and paste the code in here, and this code is using the DF Robot WT61PC library, and usually you would go to libraries and search for the library name, but you can see there is no such library in here, which means that I need to go back into the documentation and find the link to the library, which is this one, and in here I will simply download everything by going to code and click the download zip file. And then go back into the Arduino IDE and select Sketch, include library and select the Add Zip library. The next step is to select the correct ESP32 board, and if you have never used the ESP32 boards before, you have to go to File, Preferences, and then open this Additional Boards Manager URLs, and make sure to paste this line in here for the ESP32 boards, and then go to Boards and type in ESP32 and install the ESP32 by Espressif Systems. Once this is being installed, you can go to Tools, Board, ESP32 and select the ESP32 as free development module. Once you do so, you will notice that we have quite a lot of options that we can choose, but thankfully when we open the Waveshare display documentation, there is an image which shows which display should be selected. So let me just move it to the side, like so, and make sure that I have all the settings set to the same as on the screenshot. And I believe what has to be changed is to set the flash mode to be QIO 120 MHz, the flash size is 16 MB, the PSRAM should be set to QPSIRM, and all the other settings should be left to default. Since I have the display already connected to my PC using the USB-C cable, I can also go to Tools, Port and select the correct port, which in my case will be the last one, the COM number 7. And at this point, everything should be set up correctly. But before uploading this code to the display, let's take a closer look at the code itself. Again, we have some defines for the Arduino, and it looks like that if you are using Arduino, then it will use the software serial port defined on the pins 10 and 11, because the Arduino only has one serial port, and that's being used for the USB communication. However, that's not the case for the ESP32, because ESP32 has 3 different hardware serial ports, going from serial 0 to 1 and 2. And as you can see, if the Arduino is not defined, if we are using the ESP32, in that case we will use the serial port number 1 to communicate with the DF robot module. For both the Arduino and the ESP32, we will use the serial port number 0 to communicate to send the messages to the PC. So again, we will use the serial port number 1 to connect to the DF robot sensor and read the data from the sensor, and then we will use the serial port number 0, this one, to send those values back to the PC. And since we are using the ESP32 and not the Arduino board, let's remove all the Arduino references from the code to hopefully make it a little bit more understandable. So we don't have the Arduino or the ESP8266, so just delete those lines, like so, and then I will replace all the FP serial with the serial 1 instead, so serial 1, serial 1, serial 1, and get rid of this define. And then I do have defined ESP32, so I'll just use this line and not use this line. And this line is setting the sensor frequency. I believe that 10 times per second is fine, so I'll just delete all those comments. And we are left with very small code. Again, we are using the serial 1 for the communication with the sensor, and inside the setup function, we are initializing this connection with the pins D3 and D2, which I'm not quite sure what those pins are, and I believe that if I press the compile button, those pin names will not be recognized. Yep, you can see there is an error. The nice thing is that unlike the Arduino boards, with the ESP32 you can use almost any pins for the serial communication, so instead of using D3 and D2, let's use some pins that are actually being exposed on the display board. And again, if I open the documentation, there is this image which shows which pins we can use, and let's for example use pins 14 and 15 for no particular reason. So inside our code I will set the RX pin to be pin number 14 and the TX to be pin number 15. By the way, RX is for receive and the TX is for transfer. However, to connect to the module, we don't just need 2 pins, but we need 4 pins. We need the RX and TX, but we also need VCC, the 3.3 volts and ground. And again, if I look at our pin assignment, we do have grounds in here, so we have a lot of grounds that we can use, but there is actually no 3.3 volts. Because if you read the documentation or if you measure the pins, the VCs will not have 3.3 volts, but it will have 5 volts instead. So what I will do instead is I will set one of those pins into the high state, into the 3.3 volt state, and I will hope that the sensor itself will not have very big power consumption and it will work. So for example, for pin number 18, I will set it to the high state, so it will be 3.3 volts. And let's also set the pin number 21 to be low state, to be ground, because I will use just this row of pins for connecting the sensor. Again, the pins 14 and 15 are set for TX and RX for the serial communication lines. So back inside our code, inside the setup function, I will set the pin mode of the pin 18 to be output, as well as the pin number 21, and then I will use the digital write function to set the pin number 18 to the high state to the 3.3 volts, and set the pin number 21 to the low state to the ground. And I will use those pins to connect the VCC and the ground from the sensor. And I believe that at this point I have everything that I need, so I will click the upload button. Once the sketch is uploaded, let's connect the sensor to the display, and again I'm using this PCB to convert the small pin header spacing into the bigger pin header spacing, and I will position the board in a way that the USB port is facing upwards, and then connect the PCB to the very left pin header, and I will connect the ground to the pin number 21 and VCC to pin number 18. And then we did set the pin number 15 to be TX, which should be connected to RX on the sensor. And then the pin number 14, the RX, should be connected to TX on the sensor. So the final connection should look like this. Now there is nothing on the display, and that's expected because we are not drawing anything on the display, but we are sending the data back into the PC, which means that I should be able to go back into the Arduino IDE and open the serial monitor. And as I do so, you can see that I'm getting some values. I'm getting the accelerometer, the gyroscope, and the angle values. Now I'm turning it around the y-axis. I should be changing the y-axis angle, so it seems to be the case. And as I turn it around the x-axis, I'm changing the x value for the angle. So it seems like that the sensor is working, which is great. So as the next step, I don't want to send those data back into the PC, but I want to display this data on the display itself. And in my Turbo Boost Gauge project, I was using the TFT ESPI library, but I will not go to the libraries and type in TFT ESPI, but instead I will open the documentation for the display, because down there should be a link to the TFT ESPI library, which is this one. So just download a zip file and unzip it inside the Arduino libraries folder, which are those two folders. Then open the TFT ESPI folder and open this user setup select. And in that file, make sure that the uncommented line is for our display, which is this file. That's this one, the setup 207 GC9A10.h file. That's the chip used for our display. And if I open that file, which is here, the TFTI setups, and it's 207, I had to actually do one more change, and that is to include this line, this use HSPI port. Again, all the details are in the previous video about the Turbo Boost Gauge project. For today's project, I will jump back into the Arduino IDE, go to File, Examples, TFT ESPI library, and open some generic sketch, for example the gradient fill, because I already know that this sketch is very simple and it's drawing some text to the display. So let me put those two sketches side by side. And of course I want to include the TFT ESPI library and create a new object for the TFT, so just copy those two lines into our sketch. And then in the setup function, I want to initialize the display, set the rotation, fill the screen with some color, and set the font. So copy all 4 lines into the setup function. And then what I want to do is to set the cursor to some position and print some text. So just copy this set cursor position and print text into the main loop. And that's pretty much all that I need from this sketch, so just minimize it and open only one sketch. And I of course want to print the pitch and roll values, the angle X and angle Y values. And for that I will create 2 new variables of type integer and call them roll value and of course pitch value. And once we read the data from the sensor, I will set the roll value to be the angle X, so center angle X. But since this is the floating point value, I will round it to the integer value. And for the pitch value, I will use the sensor angle Y. So I'll set the cursor to be more in the middle of the screen, for example 30 and 100, and then print the pitch value, so pitch value. And just because I'm not updating the whole screen all the time, I'll just print a few of the empty characters, and I will do the same thing for the roll value. So increase the Y position to, for example, 130, print the roll label, and then the value of the roll value. And I've also changed the font to be font number 4, which is slightly bigger, and let's try uploading it to the board. And once this is uploaded, you can see that the display really shows the pitch value and the roll value, and the values go between 0 and 360, and you can see as I'm tilting this sensor, I'm changing the pitch and roll values. So the x-axis is for roll and the y-axis is for pitch, and I like how on this side it goes between 0 and 90 degrees, but on the other side it goes from 360 down to 270, and I would probably like to see it going from 0 to -90 instead. That should be hopefully a simple code change. I will just say that if the roll value is bigger than 180, in that case the roll value will be the roll value minus 360 degrees. And I will do this also for the pitch value. Let's upload it one more time. And now the display shows plus values on one side and minus values on the other side, again for both pitch and roll values. Now the values goes all the way to 180, but I don't think that you want to roll your car that much. So let's just limit those values to only go up to 40 instead. And again, this should be a quick change in the code. In the Arduino IDE, I will constrain the value using the constrain function, so roll value equals constrain the roll value to go between -40 and +40, and of course do the same thing for the pitch value, and upload it to the display one more time. And now no matter how much I tilted the sensor, it will never go over 30 degrees. Now I'm jumping in time a little bit, but later we will use those pitch and roll values to draw a corresponding image. So the pitch and roll values goes between -40 and 40, which means that I will have 80 different images, and I will draw one of those images based on the pitch and roll value. And as you've seen in the beginning, one display will draw the pitch angle and the other one will draw the roll angle. Which means that what I need to do is to send one of those values to the second display. And I've mentioned the images because I will not be sending the angle value, but instead I will actually send just a number between 0 and 80 to tell the other display which image to show. And you can send the data in many different ways, for example wirelessly using the ESP32 protocol, but since I'm using the serial communication for the sensor and serial communication for the PC, I will use one more serial communication line in between those two displays, again because the ESP32 chip has 3 different serial communication ports. But before I send anything, I will create 2 more variables, and I will call this the roll value image and set it to 0, and also the pitch value image. And those will be the images that I want to display going from 0 to 80, which means that I can calculate those values inside here just by saying that the roll image value is the roll value plus 40 and the pitch value image is the pitch value plus 40. I will initialize the serial port number 2 in the same way as I'm initializing the serial port number 1, except of course now it will be serial 2, and I might use the faster speed, which is not that much important as long as I use the same speed for both displays. And for the RX and TX pins, I believe the default RX pin is set to pin number 16 and the TX pin is set to pin number 17, which should be fine because we do have access to those pins, to pins 16 and 17, but if that wouldn't be the case, I believe that we can still remap those pins to different pins instead. So once we open the serial communication, and let's just add the command to use the serial 2 to connect it to second display. So once we start the serial 2 communication, we want to send one of those images. And let's just say that the first display, this one that we have right now, will show the pitch value, which means that we will send the roll value image to the second display. So after we print everything to the display, I will use the function serial2 print line and print the value of roll value image. So send the roll value image to the second display. Just to be sure that I'm doing everything correctly, I will also print this image value, so roll image, and I will print the roll value image. And to differentiate between those two displays, I will print some message in the setup function, so inside of setup. Let's just, for example, print the text main. And I believe that's all that we need, so let's just upload it to the display. And once this is uploaded to the display, I can tilt the sensor to change the roll value going from -40 all the way to +40 degrees. And the image should go from 0 all the way to 80, which seems to be the case. This roll value image is being sent to the pins 16 and 17, which are those two pins, but since nothing is being connected, nothing is actually happening on the second display. So let's take a second display and write a new sketch that will read the value coming from the serial 2 port and draw the value or show the value on the display. And first of all, we will connect the serial 2 pins between those two displays, the pins 16 and 17, and we will connect those in a way that 16 goes to 17 and 17 goes to 16 because RX should go to TX and TX should go to RX. I will also connect ground to ground, which is unfortunately not on this pin header, so I have to use another PCB and put it on the second pin header. And here I can connect ground to ground, which unfortunately makes this setup a little bit more messier. But we will fix this later with the custom PCB. So with everything connected, I will disconnect the USB cable from this display and connect it to the second display, just to make sure that I'm uploading to the correct display. And jumping back into the Arduino IDE, I will keep this sketch for the first display and save a copy for the second display. And since I don't have the sensor connected to the second display, I can remove all the occurrences in the code, so I don't need to include a library, I don't need to create a new object, I don't need to set those pins for the high and low state, I don't need to initialize the serial 1 connection, and I don't need to modify the frequency. I will be only showing the roll image on this display, so I can remove all 3 of those variables, only keeping the roll value image. And I don't need to read any sensor data, which means that I can remove this block of code as well. And I will only keep one of those print lines. And of course, I don't need to send anything, but instead I need to read the value of this roll value image. And there are a few different ways how to read the serial data. We can use the serial read function, and there is a sample code down here, which is looking if there is something in the serial buffer, and if that's the case, it will read the incoming byte. But we can as well use the serial parsed integer function, and it will try to read the integer value. So let's actually combine both of those, and I will copy this code which says that if there is something in the serial buffer, I will paste it down in our code. And of course the serial port is the serial port number 2. And then I will copy the serial parsed integer function, and this should read the integer value. So let's create a new variable and call this received integer and set the received integer to the parsed integer value. And again, the serial should be serial port number 2. And I'm not assigning this value directly to the roll value image because I need to make sure that this value is between 0 and 80. So I'll just say that if the received integer is bigger or equal 0 and at the same time it's smaller or equal 80, only in that case I will set the roll value image to be the received integer. And then I will print the roll value image to the display and of course call this roll image and add one more closing bracket. And maybe inside the setup function change the main text to be the secondary, just to make sure that we are dealing with the right display. Then go to tools and select the port, and it should be different from the last time. You can see that previously it was 7, now it's 15. And then click the upload button. And after uploading, we see the label secondary being drawn on the second display, but we don't see any value, which is kind of expected because the first display is not connected to the power and therefore not sending any data yet. So let's connect the USB-C cable also for the first display. And right as I do so, I see the second line on the second display and it's showing the roll value image, which is the same one as on the first display. And I can of course change the value by tilting the sensor. So if I tilt it to the left side, I should go all the way to 0. And if I tilt it on the right side, I should go all the way to image number 80. And although it doesn't look like it, we are almost done with the project. And that's because all that's left to do is to draw images instead of numbers. And again, I've done the very same thing with my Turbo Boost Gauge project, so I will use bits and pieces from that project. But first we need some images. And I've already prepared this Photoshop file, which I will open in Photopea, which is a free online graphic editor similar to Photoshop. And this file has 81 different groups, one for each angle, going from -40 all the way to +40, which means that all that's left to do is to export every single group as a separate image. And you will notice that the group name starts with -e-, which is intentional because then I can go to File, Export Layers, and check this checkbox to only export layers with the -e- in the name, and export all of those in the PNG file format. This is the content of the exported zip file, having images again from -40 all the way to +40 degrees for the roll value, but we still need those 81 images also for the pitch value. And I will actually use the very same Photoshop file and open any of those groups. And in here, I will double click the thumbnail of this GAR cage layer. So double click in here and that will open this smart object. And you can see that not only I have the car from the front view, but also from the side view. So just hide the front view and show the side view and then go to File, Save Smart Object and close this file. And suddenly all the groups has the side view of the car. But I still need to change this roll text into the pitch text. So again, open any group and double click the thumbnail of this gauge line art. And in here I will hide this roll label and show this pitch label instead. Then again, File, Save Smart Object and close this file. And that will update the label for all the groups. So I'll jump to File, Export Layers and export those layers again. And this is the content of the exported zip file, having 81 images for the pitch indicator. And once we have 81 images for pitch and 81 images for roll, we need to convert those images into the C-style arrays to be used on the display. For that, I will use a free online tool called Image2CPP, where I will first scroll down and set the draw mode to be the horizontal 2 bytes per pixel, which is this RGB565, which is a 16 bits per pixel or 2 bytes per pixel. And then scroll back up and select all our 81 images for the roll values. That will show me all the selected images, all the sizes and the preview of all the images. And if I keep scrolling down, I will go all the way to the bottom of the page and I will click the generate code, which will take a minute or so, and then click the copy output. The browser might not be responding for a while, but that's fine. And then once it's copied, let's jump back into the Arduino IDE, click those three dots and select a new tab and name this roll images.h file. Click the OK button and paste the content from the website. And there is quite a lot of data, around 300,000 lines. And we need to include this data in our main sketch by going into the main sketch and selecting the include the file named roll images.h file. Now we can easily find out how much memory those images will take on the display, because the size of one image is 240 by 240 pixels, so around 58,000 pixels, and we need 2 bytes per pixel, again 16 bits per pixel, so about 115 kilobytes per one image, and we have 81 images, which means that we need to store about 9 megabytes of data. And the good news is that our board has 16 megabytes of flash memory, so we have plenty of memory, but by default the partitioning scheme is set to default 4 megabytes, which means that, as you can see, we only have 1.2 megabytes for our application and we need at least 9 or maybe 10 megabytes. Unfortunately, none of those default options have more than 4.8 megabytes for application, again we need about 10 megabytes. So we need to create a custom partitioning scheme, which is something that I've done in my previous video about the Turbo Boost Gauge project. And I can get this partitioning scheme file by opening the GitHub source files for this project and then going to the Arduino Boost Gauge project. And this partitions.csv file is something that I need to have in our project. And we have those sizes for those individual partitions. I just need to download that file and paste it into the same folder as the Arduino sketch. And while I have the source for the Turbo Boost Gauge project opened, I will open the INO file because I need to include 2 more things inside our sketch. First of all, in the setup function, I need to call this tft set swap bytes to true for rendering the images correctly. So tft set swap bytes to true. And then I will draw the image using this tft push image function. So just copy this inside our main code, inside our main loop. And instead of drawing all those labels, I will draw a full screen image based on this roll value image index. And I only need to check if the image array is the same inside our roll images.h file, which seems to be the case, the EPD bitmap all array, which means that there is nothing else left to do and we can upload this sketch to the display. Actually, if it wasn't obvious, we need to make sure that the partitioning scheme is set to custom, and then we can click the upload button. With all of those images, uploading takes a little bit longer, you can see about 84 seconds, but once this is uploaded, we can finally see the roll image on the display, and we can of course control the roll value by tilting the sensor. You can see the movement is very smooth, there is no jumping between the values or lagging or anything like that, it's just a nice real-time feedback. Which means that at this point, it's time to do the very same thing for the first display, except of course showing the pitch value images. So let me tilt the sensor one more time and then go back into the Arduino IDE. Actually, let's open the image to CPP website and make sure that the draw mode is still being set to the horizontal 2 bytes per pixel. Then select all the exported pitch images. Again, here is the list of images, the list of all the sizes and the preview of all the images. And we want to scroll all the way to the bottom to click the generate code button and then click the copy output button. And then back into the Arduino IDE, on the left side is a sketch for the secondary display. And on the right side is a sketch for our main display. And same as with the secondary display, we'll add a new file and let's name it pitch images.h file. And I will paste the image data content in there. Then jump into the main sketch and make sure to include this file. So include the pitch images.h file. And instead of drawing all those labels down there, I'll just comment it out. And instead I will draw the full screen image, which is this TFT push image. And of course the index will be the pitch value image. The name should stay the same, but we should double check just to make sure that the array is called the EPD bitmap all array. And I probably don't need to print this information back into the PC, into the main serial port, the serial 0, so I'll just comment it out as well. I also need to go into the setup function and copy this tft set swap bytes to true, and I need to paste it in here, otherwise our images will have the swap bytes and they will look wrong. And the last thing to do is to set the custom partitioning scheme by going to Tools, Partitioning Scheme and set it to Custom. And then go to Sketch, Show Sketch folder. And do it for this one, but also for the other one, so sketch, show sketch folder for the secondary display. And make sure to copy the partitions.csv file into the folder for the main sketch for the main display. And just to make sure that I'm uploading to the correct display, I will disconnect the secondary display for now, and then jump back into the Arduino IDE, and select whatever port is in here, in my case it's the COM number 9, and then of course click the upload button. And once uploaded, we can see the pitch value on the first display, and when I connect also the USB-C cable to the second display, now we finally see images on both displays, which looks great. And of course I can tilt the sensor from left to right to change the roll value, going from -40 all the way to +40 degrees, and from front to back to change the pitch value, again going from -40 to +40 degrees. And you can see that if I hold the sensor like this, the movement seems to be kind of reversed. I would need to mount the sensor like that, or I can just change the code and just simply multiply the angle by -1. Also, if for any reason I need to mount the sensor rotated by 90 degrees, I can use the X value for pitch and Y axis for a roll instead. So everything works as expected, and we can say that the project is complete, but I would still like to show you two more things. The first thing is how to create a custom PCB, so we don't have wires sticking out everywhere and the PCB is going outside of the display. The second thing is how to use the image of your own car on those gauges, because that's the whole intention of this video, of this project, to have the gauges which are one of the kind and custom made for your vehicle. But let's start with the custom PCB, again, which looks like this, and all we are doing is we are converting those small pin headers into a bigger pin headers. And the reason is quite simple, it's just much easier to work with this bigger pin spacing of having the 2.54mm spacing or 0.1 inch. For that spacing you can get female header pins, which I haven't soldered. You can also get the male header pins, which looks like this, and you can even get screw terminals for more permanent connection. As I mentioned in the beginning, if you use the link down in the description, you can get 10 PCBs like this on the PCBWay website for free, only paying for shipping. So the only thing left to do is to actually create those PCBs. I will be using the tool called KiCad, which I have used in few of my older videos. As always, I will put links to all of those videos in the description. So let's open the KiCad and get started. Actually, let's start by opening the documentation for the display, because I want to see the image of all the pins, which is this one, and I want to convert the small pin headers to a bigger pin headers in the middle, and I want them to be in the middle because I want to still have the access for the boot and for the reset button, which are down there. But as I was thinking about it, I've noticed that if I want to connect pins like this, should be fine for the right row, but for the left row I would have to go like outside like that, and that might make the PCB bigger on this side, maybe even going outside of the display. So I've decided that I will only use one row instead of this double header pin, and it will be this left row, because here I am already using those 6 pins, and for the right pin header I will also use this left row, because here I can access the ground and the VCS pins, and even pin 13 if I want to. Those dark green pins are already used by the display, so we cannot use them. So the first thing that I will do in KiCad will be adding this single row of pins having the 1.27mm spacing with 10 pins, that's this row of pins, and then one more time for this row of pins, and those are these pins. So in KiCad I will create a new project and open the schematics editor, and in here I will click this icon for adding a new symbol. That will open this dialog, and I'm looking into the connectors generic, and I want to have 10 pins, so 1 times 10 pins. And if I want, I can even select the default footprint, and I'm looking for the pin header with 1.27mm spacing. And as I scroll in the list, I will be choosing between the horizontal and vertical, and it looks like I want to use the vertical one, so click the OK button and place it anywhere. And then copy and paste one more time, and maybe I will just rotate it around like so. And I want to label those pins in the same way as they are labeled in here. So what I'll do is I'll just make this slightly smaller and put it on the side. And then click this first pin header, right click and select edit with the symbol editor. Then select the first pin and select the properties and set the pin name to be GP36. But as I do so, nothing has changed. So I have to go to File, Symbol Properties, and make sure to check the checkbox for show the pin name. And it's being drawn over this rectangle, so I'll go there again. Symbol Properties, and increase the position offset to maybe like 3mm. Then I will select the second pin, open the properties, and this one should be GP35, and I will do that for all the pins. This message is saying that saving this symbol will only update this one symbol, which is exactly what we want. So go to File, Save, and close this dialog. And do the very same thing for the right pin header. So I will just move this image slightly to see the right pin header, which is this one. Right click and select Edit with Symbol Editor. Go to File, Symbol Properties, and show the pin name, and increase the spacing to 3 millimeters. And then again change the pin name, so this will be the ground. The second pin is VSys, and since I cannot use the arrow pins, I will just change the name to be just dash or whatever to indicate that I don't want to connect those pins, except for the last one, which is the pin number 13, so GP13, that one I can use. Save that symbol and close this window, and now we can nicely see which pins we can use. I will add 2 more pin headers, so click the Add a Symbol button, but for a bigger pin spacing, I've measured that I can only fit 8 pins, so I'll select the 1 times 8, and I can again select the footprint, but this time I will look for the 2.54mm spacing, which is this one, and again I will go with the vertical orientation, so click the OK button and rotate it with the R key, like so, so this will be the first connector, and then I will copy and paste it one more time, and rotate it by 180 degrees to be positioned like this. Before I make any connections, I would like to see how it looks like on the PCB and what would be the best way how to connect those pins together. And for that I will first annotate the schematics by going to Tools, Annotate Schematics, and click the Annotate button, then close it, and then I will go to Tools, Update PCB from Schematics. That will open the PCB editor. I will click the Update PCB, click the Close button, and that will insert those 4 header pins. And the J1 should be on the left side, the J4 on the right side, but I will rotate it using the R key on the keyboard, like so. The J2 should be in the middle, rotate it like this, and J3 should be on the bottom, like that. Now I've manually measured the positions of those pin headers, so I'll open the properties and just type in those values. So the final placement looks like this, and I can even go to View, 3D Viewer, and even if we see the error because we don't have any outline yet, we see the placement of those pins. Now as for the outline, I can of course select the edge cuts layer and then select the rectangle tool and draw a rectangle for the size of our board. And if I now go into the 3D viewer, I will see the outline of the board. But let me actually go back because I want to have the outline in a different size. I want the shape of the outline to be like this with rounded corners. And here should be the space for those labels. Now creating the outline like this is possible in KiCad, but it takes a few more steps. Because I need to actually start by drawing the tracks in the copper layer. So I'll select the copper layer, the front copper layer, and select the track tool. And as I'm drawing the track, I'm switching to the 45-degree angle, which is not what I want. So I'll right click and select the track corner mode. And it will switch to this corner mode where I'm drawing those rounded corners, but it's not very easy to work with, especially for the board outline. So instead I will right click one more time and again select the track corner mode, and this time it will switch to the 90 degrees, which is what I want. So I'll just end this track and cancel it. Actually, let me just select it and press the U button and delete this one and start drawing the outline one more time, but this time it should snap to the 90-degree increments. So I'll draw the board outline like that, and then I can select the whole track again by clicking the U key on the keyboard and again right click and select the fillet tracks, and I can select the rounded corner radius. But you can see that it's not working perfectly because some of those corners were not rounded, and that's most likely because this corner is made from multiple elements, not just 2. So you would have to tweak it a little bit in order to work, and there's just quite a lot of work to do. Sometimes you just need to select those one more time and again select the fillet tracks and enter the radius. So once I'm happy with the shape, I will select everything one more time, and then right click and select Create from Selection and Create Polygon from Selection. Hit the delete button to delete the current track, and for our polygon I will right click and select properties and set it to the edge cuts layer. And you can also see that it's not very perfectly aligned. There is this piece that's sticking around and it will definitely need some tweaking to get the right shape. So yeah, it's possible to create the outline like this with rounded corners, but it takes a lot of time. So instead of doing it like this, I will just delete it. I've created the outline in Adobe Illustrator because here I can just draw 2 rectangles, so one rectangle like this and the second rectangle like that. Then select both of those and make them center aligned, and of course combine them together. Then set the corner radius for all the corners, and we have the outline with just a few clicks. But I can as well not do that and instead use the effect, being the rounded corners effect. And if I do it like this, the advantage is that I can change the shape. and the rounded corners effect will still be there. So once I'm happy with the result, with the outline, I can export it as the SVG file, and then go back into the KiCad and select File, Import Graphics, select that SVG file, set the position to be 0 and 0 and the layer to be the edge cuts layer, and click the OK button, and we have the nice looking outline. If I go to the 3D viewer, it almost looks like the final product, except we don't have anything connected yet. Now I would like to connect those pins in here, right in the PCB, without going into the schematics, but that's unfortunately not possible, or I haven't found a way how to do this easily. So what I've done instead is I've taken the snapshot of this PCB and jumped back into the Illustrator and simply used the brush tool to draw those connections and export it as an image. And then if I go back into the schematics editor, I can insert the image by selecting Place Add Image and selecting that image. And then I can use the image as a guideline as to how I should be connecting those pins together. So let's actually do that. And I just noticed that I have the pin names on the right pin header in the opposite order. So let me quickly fix that. And now I can connect the rest of the cables by clicking the Add a Wire button. And this should go to VSys as well as this one. And this should go to pin number GP13. And once I have everything connected, I can select Tools, Update PCB from Schematics, click the Update PCB, and then I can finally connect those pins together by clicking this Road Tracks button and making all those connections. And that's pretty much all that we need to have the functional PCB. Now for my final version, I've made a few small tweaks. And this is how the PCB looks like. I've added all the names of those individual pins and some more text and logos on the backside of the PCB. And again, you can edit those labels here inside the KiCad simply by selecting the text tool. Make sure you are inside the silk screen layer and then type in the value or text, and then you can put it anywhere you want. Or you can use some other tool like I've done. I've made it in Adobe Illustrator and then imported it inside KiCad as an image using this image converter utility. There is also this copper zone on the final PCB, not being connected to anything else, and you can edit this easily by selecting this Add a Filled Zone button, and as you click, I will select No Net, so it's not being connected to anything, and then draw a rectangle like this around the board, right click and close the outline, and then select the zone, right click and select Zones, Fill All Zones, and that will fill the zone inside the copper layer. And once everything is in place, it's time to export it for manufacturing by going to File, Plot, clicking the plot button, then click the Generate Real Files, click the Generate Real File, close, close, and we should have all the needed Gerber files. Just to make sure that everything is fine, we can use the online viewer on the PCBWay website and open those files, and we can see all the top layers or all the bottom layers, or we can also show individual layers. And if I hide all of those, we have the outline and we have those drill holes. For the top layer, we have the copper, solder mask, and the silk screen. And we also have the copper, although it's not connected to anything, on the bottom layer, as well as the solder mask, as well as the silk screen with all the labels. And since everything looks fine and there are no obvious problems, I can click this Get an Instant PCB Code button to jump to the PCBWay website. But in here I need to upload a RAR or zip file, so I will just move everything into the zip file and select that zip file. And I usually keep all the settings to default except for the solder mask color. And my favorite one is the black one, which is for the same price as the green one. As for the silk screen, you can either go with black or white depending on the background color, depending on the solder mask color. But I've noticed there's also the yellow option, and I wanted to see how it looks like, and it actually looks very interesting. I mean, it's not like bright yellow color, it's more like the faded yellowish brown color. But it looks very interesting, especially with the combination of the black solder mask color. Again, this is not a matte black, it's just a standard black color. So in here, all that's left to do is to just save it to cart and order the PCB. And then of course wait a few days. Now at this point, you've seen the final PCB multiple times. So let me show you the final version with the soldered pin headers. And this one has male pin headers. And this one has screw terminals. And this is the version that I will be using to connect everything together. And I will be using the displays with the CNC enclosure because previously it wasn't possible. The PCB from AliExpress is colliding with the enclosure and you cannot push it inside. Again, that's not a problem with our custom PCB, which fits inside very nicely. So let's connect everything together, and it will be even easier than the last time because now we have labels for all those individual pins. But just in case, let me show those connections on the screen. And with everything connected and with sketches uploaded to those displays, now we have a new final version of our project. Which means that there is only one thing left to do, and it is to use the images of your own car on those gauges. Now, unfortunately, I don't have my own off-road car, but I really like those old classic Ford Broncos, and I found this website, which has nothing to do with my video except for the fact that they are selling cool-looking Broncos for a premium price. And I have to say they all look gorgeous. I really like this blue one, and the nice thing is they also include the photographs from all the different angles, especially from the angles that we need for our gauges, being this side view and the front view of the car. So let me open the side view and copy this image into the clipboard. Then open Photopea, create a new file, and the size should be set from the image from the clipboard, so hit the create button and paste the image from the clipboard. And there are many different ways how to create a selection. You can, for example, go to select menu and select subject, and here it says for a better result, press the button again. So let's actually try that. Let's select the subject again. And you can see that it really helped. Now we have a nice selection for our car, which means that now I can click this button, which is for adding a mask based on the selection. And there is very little change because the background is still being white. So let me actually add a new layer, for example, a new color fill layer, and make it a dark gray instead. And now you can see that this is with the mask. And if I shift click on the mask, this is how it looks like without the mask. So now it's properly masked. But at the same time we are missing this shadow below the car, and we can easily add it back by creating a new color fill layer, being the black color. That will fill everything with black color, but if I jump into the mask by clicking this mask icon and paste the image from the clipboard again, now we only see the content of this black layer on the white area inside the mask, so outside the car, and we don't see the content on the black areas, but we want to make the opposite, so I will click the Ctrl-I for inverting the mask. And as you can see, now we have a nice shadow. We also see the faded car, but that's not a big problem because it will be covered by this car layer. And so this will be our final image that we want to show on the gauge. So let me actually select both layers and create a copy, and then merge those together to have just one layer. And let's call this side view. Then I will open the pitch and roll gauge Photoshop file and open any of those groups and open the gauge car layer. That's a smart object. And we want to copy this car into this file, into this smart object. So from here I will take this layer and move it over this gauge car PSD file. And obviously it's way too big, so I'll press the Ctrl-Alt-T button, or I can go to Edit, Transform and Scale it to much smaller size. For example, I don't know, like 20 or 19%. Click the OK button, hide this car. And this yellow line is not quite matching the theme of the car, so let me just double click it and add a new color overlay. And for example, go with white color instead, so click the OK button and then save the smart object and close that file. And now we have a new car for all those pitch images, but it's still saying roll. So let me open this again and open the gauge line art and show the pitch label instead of the roll label. And maybe change the color as well, so apply the color overlay and maybe use some kind of blue color instead. Then File, Save Smart Object and close this. And while I'm changing colors, I would like to also change the color of the text on the bottom as well as this trail below the needle. And the trail should be simple because that's this layer, so double click it, double click the layer to open the layer style and apply the color overlay. And instead of using the blue color, let's for example go with some grayish blue color or maybe this yellowish one. Hit the OK button and OK button, then File, Save Smart Object and close that file. And the last thing we want to change is the color of this degree label, but that's not a smart object, that's just a standard text label, which means that I will double click the layer and then apply the color overlay, which is already being applied, but this time I will use a blue color instead. And I need to use the very same color overlay layer style for all the text labels, because you can see now it's orange still. I need to copy this layer style, so right click layer style copy and paste it for all the other text labels, so select those and right click layer style paste. And I've only pasted it for those two labels, so this one is also orange, but thankfully there is an easy way how to only show the text labels. If I click the filter and then I click this T icon, I will only see the text layers, but I still have to select those one by one with the Ctrl key being pressed, so let me just do that. And then I can right click and select layer style paste. Once I have the new color applied, I can get rid of the filter. And I just need to double check that all the labels have the correct color. And here I have one which doesn't have the right color, so let me just fix that. And now it should be fine. You should already know the next steps. I will go to File, Export Layers, and export all those groups as individual PNG images, and the content of the zip file looks like this. Then I will open the image to CPP website, and before selecting the images, make sure that the draw mode is set to the horizontal 2 bytes per pixel, and then select all the images. Here are all the images, here are all the sizes, and here are all the previews of those images. And down there, click the Generate Code button, and then click the Copy Output button. Jump back to the Arduino IDE and open the sketch for the main display, and jump to the pitchimages.h file. Delete the current content and paste the content from the generated images. Then make sure that the correct display is connected and select the port and click the Upload button. And after a minute or so, we indeed see a blue car instead of the orange car for the pitch indicator. So let me finish the project by using the very same car also for the roll indicator. And it should be quite simple because we already have all the colors in place, we just need to use a new image of the car. And for that I will jump back into this website and open this photograph and copy it into the clipboard. Then jump back to Photopea and open this image and actually hide this layer and paste the image in there. That's the front view. And I will use the very same method for getting the selection of the subject by going to Select Subject. And then I will do this one more time, so select Subject one more time. And once I have this nice looking selection, I can add the mask by clicking this icon, which is for adding the raster mask. But I can as well go to Layer, Raster Mask and select the Reveal selection, that will do the same thing. And if I show this gray background layer, I can see the alpha channel nicely. Again, this is without the mask and this is with the mask. I still want to have this shadow, so I will create a new layer, and that will be the layer type of color fill. In the black color, click the OK button. And let me actually hide everything else and jump into the mask layer by clicking this thumbnail and then Ctrl V to paste the content from the clipboard one more time. But same as the last time, I will click the Ctrl I to invert the selection, move this layer below the car layer and show it. And now we have both the car and the shadow, which looks like this. So I will select both of those layers with the Ctrl key being pressed, and then create a copy by duplicating the layer, and then merge those either by pressing Ctrl E, or I can as well go to Layer, Merge Layers, and this will be our front view. Then I will open this second Photoshop file and open any of those groups and double click the thumbnail of this Gauge Car Smart object. And from our first file, I will select this front view layer and move it over this gaugecar.psd file. But this layer is way too big, so what I will do is I will go to Edit, Transform, Scale, and scale it down to maybe, I don't know, like 22 or so %, maybe actually slightly bigger, like 24 maybe. Make sure it's somehow centered, and then go to File, Save the Smart Object, and close that file. And now we have a new car for all those individual groups. I will again open any of those groups and open the gauge line art. And instead of showing the pitch label, I will show the roll label, which is still being orange. So copy the layer style from this one and paste the layer style for that one. Then File, Save the Smart Object, close that file. And we are ready for exporting those as PNG images. So File, Export Layers, and click the Export Layers button. And this is the content of the exported zip file. So for the last time, let's go back to the image to CPP website, change the draw mode to be the horizontal 2 bytes per pixel, select all our roll images. Here's a list of images, list of sizes, and list of previews. And down here, click the Generate Code button. Then copy the output into the clipboard. In the Arduino IDE, open the sketch for the second display and open the roll images.h file, the header file, delete the content, and paste the new content. Make sure that the second display is connected with the USB-C cable and select the correct port, and then click the Upload button. And after a minute or so, our project is complete. You might have noticed that now I have the USB port on the bottom side, and that could be easily done by setting the value of the set rotation function in the setup function. You can also buy a lot of USB-C adapters, one of them being this one, which fits the display nicely, and then you can connect the USB cable behind the display so it's not that much visible. Also, you can probably use the USB adapter to somehow glue this or screw it to your dashboard. Or you can of course 3D print your own case, but that's probably something for the next video. And that's pretty much it for today. If you have any questions or comments, please put those down in the comment section. As usual, all the source files are on GitHub. If you create your own version of the gauge, please let me know, I would love to see it. If you like this video, please check my channel because I have a few more which are covering the similar topics, that is using displays inside a car. Thank you very much for watching and I hope to see you soon. Thanks and bye.